So in the last lecture, we were discussing localized MO theory, where we saw that how MOs developed using localized theory start with valence bond kind of approach, where we start with the hybrid orbitals of the central atom, and then we go on develop MO theory. But one of the major issue was that there was accidental degeneracy of those MO orbitals that we saw. Let us now see how delocalized MO theory works better, and it yields energies that are much more consistent with the electronic spectra and ionization energy of a molecule. So let us start our discussion today with delocalized MO theory. So or MO description of chemical bonding. So we will see that these delocalized MOs yield energies that are consistent with, or we can say more consistent with, electronic spectra and ionization energies. See, using group theory, you cannot calculate the exact energy, but you can only tell the relative stabilization, destabilization of different orbitals. We will see that today. So for calculation, of course, you will have to set up the actual equations and solve the integrals. And some of the integrals you get help from group theory rules, that some of the integrals will get cancelled out. So that is the only help group theory will do. But for actual calculation of energies, you can use this theory to calculate the energies, which has to be explicitly calculated. Okay, so group theory will not help you calculate the actual energy numbers. Okay, so this particular approach requires abandoning the VB or valence bond notion of chemical bond. What is that notion? That the electron pairs subside between the shared atomic orbitals or between the interacting atoms, right? Chemical bond, that is a chemical bond as the sharing of a pair of electrons by two adjacent atoms. Okay, so this thought we have to get rid of when we are discussing delocalized MO theory. So what we will do instead of VB notion, so in this approach, we try to find out bonding, anti-bonding, and non-bonding. So idea is still, the aim is still same, that we need to find out bonding, anti-bonding, non-bonding orbitals. But here it is done as the linear combination of atomic orbitals of ordinary atomic orbitals on all atoms. So there is no hybridization to start with. All atoms of the molecule. So explicitly we will just write hybridization, which is actually the product of wave functions, right? So that is not a starting point here. So this has to be very, very clear. So what is the approach? So I'll just give you a brief approach, and then we'll write down step by step, and then again we will take the beryllium hydride example so that we can compare it with localized MO approach. So the approach in short is match the symmetry of central atom, for example in MX4 type systems, right? With, so you already know what is the atomic orbital of central atom, so you have to match the symmetry of that central atom atomic orbital with that of linear combination of orbitals of outer X atoms. So these outer atoms, like this one is called as central atom, this M is called as central atom, and X is called as pendant atoms. Okay. And we have seen this approach. These are called as SALCs. So we create SALCs using outer X atoms, and then we match the symmetry of central atom with those SALCs and combine them to form molecular orbitals. So thus we can write, let's say if this is the wave function of molecular orbital, so we can say that this is a combination of course, symmetry matched combination of atomic orbital of central metal atom or central atom and plus minus any combination with appropriate coefficients with SALCs of nx atoms, right? So this is the general picture of MO theory, where we can say that the psi SALCs is nothing but C1 psi 1 plus C2 psi 2 plus Cn psi n. So this is a linear combination, right? This can be plus or minus, all right? And the appropriate coefficients also have to be, and then these again have to be normalized and orthogonal, all those things which we have already learned. Okay. So where is the group theory application coming in? So using group theory, so we say that we use group theory rules to determine the symmetry of possible SALCs formed from pendant atom atomic orbitals. So let us again compare this with valence bond approach. So in case of valence bond approach, we did not do SALCs like this. So instead what we did, we picked up the atomic orbitals of central metal atom or central atom, and then we created the hybrid orbitals of those, and then we matched the symmetry of those hybrid orbitals with the atomic orbitals of pendant atoms, right? Pendant atom atomic orbitals, and those were matched. In case of localized, what we did, so we did hybridization here at the central atom, and we did the SALCs of the external, and then we matched the symmetries, right? In case of MO theory, we are taking atomic orbitals here and we are creating SALCs of pendant atoms, and then so there is no hybridization involved here. So in delocalized MO, that is the basic difference. Okay, all right. So maybe in the end we will just write down the summary of all three so that it is very, very clear. But let's go on with what we were saying, that how group theory rules are used in MO approach. So group theory rules to determine the symmetry of possible SALCs formed from pendant atom atomic orbitals, and then determine the SALC that will combine with which atomic orbital, of course this is on central atom, to form MOs. Okay, so let us define the steps one by one on how to proceed with this. So let's see. So use directional properties of potential or potentially bonding orbitals on the outer atoms or pendant atoms. In some books you will see it is written as outer atoms. In some books it will be pendant atoms. This will be shown as vectors. We will see that when we'll describe it as a basis for representation of the SALCs. In the point group of the molecule. So we will explicitly see what it means, but let's first list down what we are going to do so that you have some idea of this thing. So second step is, once you have determined what is the basis you are going to take, then you will generate a reducible representation. Generate a reducible representation for all possible SALCs. And this we will not write explicit matrices under each symmetry operation. We will simply do this by noting which of the vectors are shifted or not shifted by each class of symmetry operation of the point group. Okay, so once you have generated the reducible representations, what will be the next? Next, we will have to decompose the reducible representation. So decompose the tau reducible into its component irreducible representations. Now this can be done using reduction formula or by inspection. If it is an easy case, you can just simply do it by inspection or by inspection of character table, like we did in the case of D infinity H, where using reduction formula was not as feasible, so we simply did it by inspection. Okay, so next is, what is the next step? Now fourth is determine the symmetry of potentially bonding atomic orbitals on central atom. And this is done by inspecting unit vector and direct product transformations. For example, if you are looking at the symmetry of px orbital, then you have to see that what is the symmetry of x unit vector transformation. And if you are looking for a d orbital symmetry, so corresponding direct product of xy has to be taken in consideration, right? transformation. This is, of course, you have to look at the character table, listed in the character table. So next step would be central atom, atomic orbital, and pendant atom SALCs with the same symmetry will form both bonding and anti-bonding. Okay, you can say anti-bonding MOs or else, or we can say linear combination of atomic orbitals MOs, because this is a linear combination. There is no product involved here. Again, so central atom, atomic orbital, and pendant atom SALCs with unique symmetry. Let's say some of this cannot match, so those will be with unique symmetry will remain as non-bonding. That is very obvious, right? Non-bonding. So this should be very, very clear. So now let us take the example of BeH2 again. We have already discussed this example in localized MO theory. So now let's see what is the difference when we take delocalized MO theory. Okay, so we said that we have to start with directional. Let's see, we have to. So the first step is use directional properties of potentially bonding orbitals on the outer atoms as a basis for representation. So what is that directional property? What do I mean? Okay, so we will say for sigma bonds, use arrows pointing along the internuclear axis. And for pi bonds, use arrows perpendicular to the internuclear axis. For example, if you want to consider the case of CO2, let's say, then the directional property would be something like this. Okay, so you have to consider these arrows. So we'll draw it on here. These arrows as the basis set. Now these are the two outer or the pendant atoms, and this is the central atom, right? So we are considering the formation of SALCs using these two orbitals, which are the pi orbitals of this. Now you have to consider perpendicular arrows which are perpendicular, but for sigma bonds you have to consider like this. Okay, so these arrows are for sigma bonds and these arrows are for pi bonds. Okay, so this should be very, very clear. Now for in case of BeH2 we only have sigma bonds, so we will consider BeH2. So we will consider only these arrows which are along the internuclear axis, and we will use these two arrows to create a tau reducible under D infinity H point group. So let us see what do we have. So D infinity H point group E 2 infinity phi infinity sigma V I 2s infinity phi infinity c2. Okay, this we have already seen. So this is tau reducible using these arrows as the basis, and under E these arrows would not change. Under C infinity also these arrows would not change. So we'll get to sigma V, the arrows would not change. I, the arrows, both the arrows will change. 0, 0. Okay. Now this tau reducible, by inspection it reduces to sigma G plus plus sigma U plus. This also we have seen in the last lecture. Now either you can apply projection operator, or you can again by inspection you can do that, but standard in this particular case it is difficult to apply, but you can still do that. So apply projection operator for the two IR representations on 1sa and 1sb orbitals of HA and HB. See, actually you don't need to apply projection operator, because if you are combining 1sa and 1sb, you know that if you combine these orbitals in 1:1 ratio, you will get totally symmetric, and if you subtract one from the other, you will get sigma u as the basis. So you can just simply do that, or you can go methodically and then you can actually apply projection operators, which will be difficult, but you can still manage to do that. So if you do that, summation G plus applied on 1sa, you will get after normalization 1 by root 2 1sa plus 1sb, right? And we can call this set of SLCs as phi g. So G, because this is coming from Girard symmetry. Okay. Now again projection operator from sigma u plus applied on 1sa or 1sb. You can apply on any of this. After normalization, it will give you 1sa minus 1sb, and this we will call as phi u. Okay, this is just for nomenclature. All right. Now what happens? We can also draw this pictorially. So pictorially, this will be easy to see. SALCs can be represented as, so you have phi g, which is plus, this is 1sa combined with plus of 1sb. So same phase of the two orbitals are combining to give you phi g. Whereas opposite phase, which is represented as plus and minus, this has nothing to do with electronic charge or something. So this is plus, this is just the phase of the wave function with a negative phase. Okay, this is again 1sa and 1sb. Okay,